Okay, we're working on page 9 at the bottom of 8.7a. So let me just recap real fast what we did here. So solving a logarithmic equation, I should say. Step 1, put all your logs on the left of the equal sign, and you can see they both started on the left, so step 1 is done. Step 2 above in the box says write as a single logarithm. And we learned in 8.5 that subtraction goes back to a single log of division. And so the positive argument or positive logs arguments in the numerator, negative logs arguments in the denominator. And then step 3 is to write as an exponential so I can solve it. So that's loop and swoop. So we always start with the base of the log becomes the base of the exponent. We go over here to find the exponent, and then we set it equal to the argument. And then from the example above, we learned that if one side is a fraction, make the other side a fraction. So 2 to the 4th is 16, so I made it 16 over 1. And then we can cross multiply and set the two cross products equal. So this cross product would be 16 times x minus 5, and set it equal to this cross product, which would be 3x minus 2. So that leaves me 16x minus 80 equals 3x minus 2. We want all of our x's on the left, so subtract 3x, subtract 3x. We get 13x minus 80 equals negative 2. And then add your 80 over, add your 80 over, and you get 13x equals 78. Divide by 13, divide by 13, that gives us x equals 6. I think 18, yep, 6. So it would be nice if we could say, yay, we're done. But remember how we have to plug that 6 into both arguments and make sure that it checks. And there's only 2 arguments because there's only 2 logs. So you can do a visual check. You just have to make sure it's positive. So put 6 in there. 6 times 3 is 18 minus 2 is 16. Is that a positive number? Yes. Then put 6 in here for this x. Is 6 minus 5 a positive number? Yes, it's positive 1. So since it made both arguments positive, one it made 16, one it made 1, since they're both positive, then we go up here and in solution sets show that it's a valid solution. Had it made one of them 0 or negative, then I would have had to throw it out and write no solution. But it made them both positive. This one turned out to be 16, this one turned out to be 1, so it's a valid solution. And you know I'm going to put 1 on your test that doesn't check, so make sure you check every log problem you ever do. Okay? Okay, let's go ahead and look at page 10. Got a couple more to practice on. So this is the last page of 8.7a. So it says solve the equation. I see it's a log equation, so that means I have to follow the steps on page 1, or actually page 9. So page 9, step 1 says put all your logs on the left. Well, look at, they already are on the left side of the equal, so I'm good. Step 2 says write as a single log, and it doesn't matter if it's a natural log or a regular log, you still have to write it as a single log. So we learned in our last section 8.6 that it doesn't matter whether it's a natural log or a log base E or log base A or log base 10, they all follow the same rules. So addition goes backwards into a single log of multiplication. So addition goes backwards into a single log of multiplication, and that's what I have here. So I write the word log once, and I multiply the arguments. So that's what we learned in 8.6 is all the properties of logarithms. So addition goes backwards into a single log of multiplication. So step 3 is write as an exponential. And like I said, this is where almost every student that misses this problem stops. They're like, what do I do next? But we don't know how to solve a log. So you have to get it out of log form. You get it out of log form by doing loop and swoop. So if there's no base there, you have to put the base in. And remember, natural logs are always e. So loop and swoop produces e to the 0th equals 2 times x minus 1. So that was easy, right? But now can I solve it? Look how easy it is to solve. But when it's a log, I have no idea how to solve it. But now that it's an exponential with no log in sight, boom, anything to the 0th is 1. I distribute, solve for x. Done. After I check, of course. So just remember from our last section that if you see a natural log, its base is e, so you put that in just like if you see a log, like on the front page when we saw a log that didn't have a base, we put a 10 in. On natural logs, we put an e in. All other logs will have their bases written down. So the base of the log becomes the base of the exponent. The number over here is the exponent, because remember the definition of log is it's just an exponent, so you know that has to be the exponent. And then you set it equal to the argument. So I'm going to do a couple things on this step. Does everybody agree this is going to turn into 2x minus 2? And we're going to put it on the left, just because I like having my x on the left. And set it equal to anything to the 0th power we learned in chapter 4 is 1. It doesn't matter whether it's pi to the 0th, e to the 0th, x to the 0th, 2 to the 0th. Anything to the 0th power is 1. So 2x minus 2 equals 1. Now we can easily solve for x. 2x equals 3, so x equals 3 halves. And now all we have to do is check and make sure it makes the arguments positive. So does everybody agree 3 halves is 1.5 or 1.5? It's a little bit easier to plug it in that form. So this log doesn't have an x, so obviously I don't need to check it there, but this one does. So plug in 1.5. Is 1.5 minus 1 a positive number? Yes, it's 0.5. You can't do it in your head. 1.5 minus 1, that's a positive number, 0.5. So as long as it makes it positive when you plug it in, that means it's a valid solution. So you could write 3 halves, you could write 1.5, you could write 1.5. Any of those would be correct. But it was easiest to plug it in that form, so that's why I changed it to 1.5. So, since we only have 3 of these to practice on, and you're going to have to do these on your homework tonight, I would shut the video off now and see if you can do 3. It's the easiest of the 3. So, shut it off and see if you can do that one. So, notice all the logs are already on the left. There's only one log. Step 2 is write as a single log. It's already done, so that's why I said this was the easiest one, because step 1 and 2 are already done. So we're on to step 3 where it says write as an exponential. So I immediately put my base in and I do loop and swoop. So e to the 9th equals, so the base of my log becomes the base of my exponent. The number over here is my exponent, and I set it equal to the argument, which is square root x plus 6. So that's looking a little funky, right? So it combines a little bit from this section with stuff you've done in previous chapters. Do you remember how to solve a radical? First off, I'm going to flip it over because you know how I like my variable on the left. So a lot of students are tempted to put that in the calculator. Don't do it. Do you see any problem that says round? Does it say round? No. Does this say round? No. Does this say round? No. The minute you put it in the calculator, you're going to have to round it because E goes on forever. So if they don't say round, that just means you leave E to the ninth in the problem. So now you need to say to yourself, how am I going to solve for X? Oh, I remember. I need to undo the square root. So I undo a square root by squaring both sides. So these will now cancel each other out. And you'll get x plus 6 equals, and this is why I love this problem because it has so many chapters of stuff in it. So the E we learned in chapter 8, radicals we learned in chapter 6, exponent rules we learned in chapter 4. So it's like a bunch of chapters all in one. So what do I do with those exponents? Add, subtract, multiply, divide? So is it a multiplication problem? No. So I don't add the exponents. It's a raising to the power, and in raising to a power, we do multiply our exponents. So this would be 9 times 2, e to the 18th. So we don't square it, we multiply. It's like this one, a cubed squared is a to the 6th. Same exact rule. Just we have an E, which is the base, which remember E is about 2.7, so it's just like any other number, just goes on forever though, like pi. But we're using the same rule here as we did here. Okay? So again, remember I'm solving for X, so to solve for X, you have to keep your eye on the prize. You're trying to get X alone. So I get X equals e to the 18th minus 6. And we call this an exact answer. So if the directions don't say otherwise, as in this, all it says is solve, that means they want an exact answer. Once in a while, I'd say about 50% of the time, they want a rounded answer to or instead. So I want to show you how to do both. Like all these other ones were already exact answers, so we didn't have to worry about it. But if they don't have anything in the directions, you give an exact answer. But if they say round your answers to 2 decimal places, then you would type it in your calculator. So I'm not going to box this one because it didn't say that. The directions just said solve, so this is the answer they want. But on Alex and on the test, sometimes they'll ask for both. Sometimes they'll just want the exact. Sometimes they'll just want the estimated. So you should be able to do it in both forms. So you just evaluate on your calculator. Remember, second ln is e. Type in 18, close your exponent, and do minus 6. So, woo! I guess we can't really round that one, can we? Because it already stops at 2. It doesn't really stop. It ran out of places. So it would be 65,659,000 963.14 if it said round to 2 decimal places. And again, it would tell you what to round to if it wanted you to round. So if it doesn't say the word round, don't touch it. You just write it just like that. But students love to type that in the calculator right at the beginning. They write like right there, they change that with a decimal. Don't do it. Don't interchange it with a decimal unless it says to round. And this one didn't. So this is the answer you would type into Alex. Or type into your test. Or write on a paper pencil test. Because there was no rounding asked for, so that means they want an exact answer. And we'll start the bottom half of the page on the next video because we just have about 15 seconds. So I'll see you in a bit.